Thank you. Good evening, ladies and gentlemen. First of all, I would like to thank the Tech for Impact team for putting such a nice venue here. So I would like to share some of our technologies here. So the title of our technology, the name of my technology is perovskite solar cells. So we call it a new paradigm in energy sector. If we take this energy, we have plenty of solar energy to convert. Silicon solar cells are there. Silicon solar cells, what we are having is, it's very energy intensive. You can see in my presentation, but the technology which we have developed is very inexpensive. You can see in my presentation, it's just the inks, 1 kilogram of ink, you can produce 1 megawatt of power. That's the power of this technology. So this project we submitted jointly with Professor Paul Dyson and my colleague, Dr. Cristino. So we are working at EPFL, and Paul Dyson, myself, is leading this project. So the technology is shown on the right side. This is a very simple technology. You have a material encapsulated between the two conducting glasses. So what it does is it absorbs light, it creates the charges, we have to extract at the interfaces. That's all we have to do. And then the extraction process is so efficient, you can almost collect all the photons which you are shining the material, and you extract all the charges. And the another beauty of this material is it's a dual function. So future of displays can be using this material. So we can change this material property. That's a particularly typically this type of compound, ABX3. This is a salt. A is some kind of a cation. This can be a cesium inorganic or organic. B can be lead or tin, or X is a halide. By changing the halide, we can change the material properties emitting from red, that's iodide, to green, that's bromide, and to blue by chloride. So this way, what we can have is same material absorbing sunlight, giving you the electricity. Now we inject carriers into the material that gives you the light depending on the material, depending on the material which you are incorporating here. So the beauty of this material, you can see from the absorption spectral properties, it absorbs all the visible light from 400 to 800 nanometers. So showing when the light falls onto this material, it attenuates all the light, so converting into electricity. And then you can change its band gap material by tuning its properties either by a cation or by changing the halide. So the power conversion efficiency in the world is reaching close to 23% efficiency. We ourselves, we have reached 22.5% efficiency. This has been certified in international laboratory in Newport at USA, and these efficiencies are comparable to silicon solar cell efficiencies. Depending on the manufacturer, silicon solar cells, you have it between 22 to 24% efficiency. But the difficulty with this technology is energy intensive and technologically challenging. Whereas our material is very simple to process. In fact, you can print. Imagine tomorrow you want to convert all our news printing machines into solar cell printing machines. Then we can supply energy required to the whole world, planet, without any problem. So this technology, we can also print by using normal printing methods. So I'm comparing a silicon solar cell technology versus the new technology which we have developed. So this new technology, you can produce locally. You don't have to import from China. Transportation charges are very expensive. You can produce locally and still reach very high efficiencies similar to silicon solar cells, which are during the 60 years period, we have reached 24% efficiency. Only last 6 years of this new technology, we have already reached 24% efficiency. And the cost, it's 2 cents per kilowatt hour. To give you an example, we pay 21 cents per kilowatt hour in Swiss. This, if we install our technology, we can reduce the cost of 2 cents per kilowatt hour. In addition, if you take the silicon solar cells, it's not free. What we are having is, we are producing a lot of carbon dioxide. How do you produce carbon dioxide? Because you get the silicon dioxide, you reduce, you make a metallic silicon. So you have a lot of carbon dioxide generated by this material. On the other hand, our material is carbon dioxide free. So if you look at the statement last week, Energy Secretary, Stephen Chu, what he said is, if the renewable energy cost falls at close to 1.5 cents, then we can start hydrogen economy. So what it means is, you have electricity, and this electricity you can use to electrolyze water to produce hydrogen, which is storable, because solar energy is intermittent. So here is the drawbacks. If you look at the challenges, this is our material which we are talking. This material has a challenges, that moisture, it's a sensitive, and oxygen also, it decomposes the temperature. However, in collaboration with Paul Dyson, we have developed materials which can address these issues. Here is the new ionic liquid material, which has a fluorinated compounds. It acts like an umbrella for these materials. At the same time, we have another material which polymerizes and making it extremely stable performance up to 3,000 hours. So we have issues, and we have addressed this within the lab. So if you look at the total energy consumption for fabricating these perovskite solar cells compared to silicon solar cells, it's order of magnitude lower. This is a perovskite solar cell energy, primary energy input. This is silicon solar cells energy, primary energy input. And it's an order of magnitude lower. And if you take the energy payback time, for silicon solar cells, it can be close to 1 year or 1 year. And for perovskite solar cells, energy payback time is less than 2 months. So you can have a perovskite panels like this one and produce enormous energy, and that can be used for the electrolysis of water. So you produce hydrogen. The hydrogen can be stored in metal hydrides, and this you can reuse it in fuel cells, and then it's a cycling. At the same time, when you have such an excess of energy, you can also use for reverse osmosis, and that's actually addressing sustainable goal of 7, SDG 7. So you make use of this energy to do the reverse osmosis to purify seawater into drinkable water. That's all my presentation.